All right, next topic. Dr. Jon Schoonover, Southern Illinois native, has been at SIU over the past 14 years, got 2 degrees from SIU, and then got his PhD at Auburn. Each year he teaches 2 soils courses, 3 water resource courses, and a tree identification course. Primary research has always been involved working with farmers to develop and manipulate ag best management practices to maintain water quality. And Karl Williard, professor of forest hydrology and watershed management. I don't know if I would have taken those classes when I was, I don't know. BA in biology from Lehigh, MS in environmental pollution control from Penn State, PhD in forest hydrology from Penn State, teaches undergrad and graduate courses in watershed management and hydrology at SIU-Carbondale. John, take it away.
Today we're going to talk a little bit about the impacts of agricultural BMPs on water quality. This is going to be a pretty fast-paced talk because we've got 3 different talks wrapped into one here, so we're going to fly through these pretty quick. But Dr. Williard will be up here in just a second. So our NREC-funded research, this picture is also a couple years old. It's hard to get all our grad students and our researchers together. A few of these folks have left. A few of new ones have came over the years. But we're going to talk about the long-term impacts of cover crops and tillage on soils and water quality. We're going to talk about stream bank erosion and some of that legacy P. WASCoB research that we've been doing, a couple different projects. Our saturated buffer research, we've had a couple different projects on that as well. And then the last thing Dr. Williard will talk about will be his gypsum research. So some of you have heard this before, but the saturated buffer research we've done so far to date, we started down in Massac County with a 2-stage buffer design. And our goal has always been to kind of expand the area that these saturated buffers can be used, because the area that they can be used is pretty small in the state of Illinois. So we've been trying to add these different retrofits to try to get them to be, like I said, have a wider span of use. So this 2-stage buffer basically had 2 control structures, so we tried to divert more water. So we had it come into a first control structure, then it diverts down the lateral lines into a cover crop or service crop. And then it goes into the second stage, and then it goes into a grass buffer. So one of the things we found from this study is, as Dr. Ford talked about, the water table being that close to the surface a lot of times. So as that water table would rise, the lateral lines that were in the saturated buffer would actually feed back into the control structure, and we were generating water. So we had X amount coming off the field, more came in from these laterals that are supposed to be taking it out, and we generated more water. So that's just when the water table came up. So what we did in the second design is we also tried to get more water out on the field. Instead of going 500 feet laterally, we did a pitchfork design where we had 3 dispersion lines that went out laterally. So we got 1,500 foot of dispersion or dispersed water. And we also installed a backflow valve, and I'll show you a picture of that earlier. But once the water, or in a little bit, once the water goes out, it can't come back in. So we were going to compare inflows and outflows, compare nitrogen and phosphorus, and identify the site and hydrologic characteristics that are driving these systems. So our second study with the pitchfork design was up in Moultrie County. This is right off the banks of Lake Shelbyville. So right where the West Okaw and Kaskaskia come together, we're sitting right there in a field that's tile drained. So the water's coming in, the pitchfork design, shooting it out to one side. We have a side-by-side comparison on that site. So we have a standard saturated buffer. You can see it on the left side. And then on the right side over there, you got this pitchfork design. And if you look at the control structure on the right, you see the 3 chambers, just like any other saturated buffer. It's going to come in. We have a V-notch weir in there so we can take the tile stage and calculate discharge. And then it goes over that one, disperses out the pitchfork design, and then comes over another weir so we can take stage to see how much water has been lost or diverted. So here's a close-up of our actual picture showing that backflow valve that prevents water, and it's basically just a flap. Once the water goes out, it can't come back against that flap. And then the third line I didn't mention out in the field also has this gate valve. So we can shut that valve on the third line, the one that's closest to the field edge, to allow the farmer to get in there a little sooner. We can kind of dry it down out there on the edge of the field first. So like I said, this was out on Shelbyville Lake, and if you look, this is an aerial photo that Mary and Mark took with their drone back in 2019, but you can see Shelbyville Lake in the background right there. So we are literally sitting on the edge of the lake. So what we've seen so far in terms of flow diversion, like I said, that water table's coming up, so you can see water was actually being increased in the outflow. In the standard design, in the pitchfork, it's going down. And you can see the number of days it flowed was about 29 days, 29% of the time in 2000. And then 2001, it flowed a little bit more often in that system. So in terms of nutrient reductions, it was cut by what was reported was about 40%. So we're about 33% in terms of nitrate reductions on these saturated buffers. DRPs, about the same, about 50% reduction in some of those situations. Some of them didn't see any reduction at all in either the pitchfork or standard buffer design. You can see in the groundwater wells, we had wells at the field edge and then successively through the different buffer strips. And you can see that the water is being dispersed out there. There's a little bit higher concentrations in that saturated buffer or the pitchfork design where the wells kind of overlay those lateral lines. So where that water is being dispersed out, you see an increase in the concentration. So to summarize this, the pitchfork design did outperform the other in terms of both nutrients and water. The water, once it came out, it didn't come back into the system. The backflow valve, again, I've talked about this before, but it seemed like it had a very significant impact. Once that water went out, it couldn't come back. So we did see, if you're seeing reductions in water that's going out, you're also going to see reductions in loads going into the stream. And then our long-term goals with this, we've got a partnership that we've developed with the Land Improvement Contractors of America, Illinois Farm Bureau, USDA, and the NREC and the NRCS to try to install one of these saturated buffers over the next 5 years in each year and tweak the design a little bit. We're looking at one right now just east of Springfield, and on the drive up here I saw a field that looked perfect that they just put tile in, so I was on my Onyx map getting landowner names on the way up here, so we're going to have to look into that one. And then talking about the WASCoBs, we've done this for a little while as well. We've got a project up in Menard County that we're looking at WASCoBs, and then we're having another one this year that we got funded where we're going to look at WASCoBs in southern Illinois. And when I'm talking about a WASCoB, I'm looking at a dry dam with the basin out in front of it. So we had a field day back in 2019 up at the Menard County site. Our objectives were to compare cover crops and these WASCoBs in terms of nutrient renovation. So one of the things that hasn't been done a lot has to take a closer look at how these impact water quality. So then we're going to just look at all these different metrics, and I'll get into each one of those in more detail as we move along here. So here's the Menard County site. We had 4 WASCoBs we looked at, or 4 catchments. Each catchment had 2 WASCoBs if it was a WASCoB treatment. So it had one with cover crops, one without cover crops, and then we had an ephemeral gully with cover crops and one without cover crops. So we did this side-by-side comparison again. So here's the pre-2017 photo on the left. Here's the USDA NRCS map that they created and their plan moving forward. And then here's the completed WASCoB once they were installed. And you can see on this field, this was only a 40-acre field, and there's quite a few WASCoBs or dry dams established in it, and they moved a lot of soil to make these. So this is going to come into how much do they actually impact crop yields. So in most situations, not 90% of the field is impacted by the WASCoB. So at the end of the ephemeral gullies, we looked at water quality, and we also looked at the stage so we could calculate loads again from those concentrations. In the ephemeral gullies, we'd put these partial flumes in there, and they have a known sampling area, and based on that area, we can convert that to a discharge to calculate those loads. We also had ISCO automated water samplers. They just had 24 bottles in them, so we could collect samples during storm events and actually look at the rising limb, the peak, and the falling limb during that storm. Same thing at the outlet of these WASCoBs. So instead, there's no open channel or stream, so we're trying to sample a tile. So what we did was put in a control structure with a V-notch weir in it again, so you could calculate discharge. Again, we had the ISCO with the 24 bottles doing the sampling up there. And then we also had these stack pole samplers over to the right. And you're going to see that we've kind of tweaked these over the years, but they were designed, we put them in the actual basin. As the water would rise in the basin, those bottles would fill up. There was an air tube and a water tube, so the water would come in, the air couldn't escape, then it just retain a snapshot sample in time. And then some of the challenges we had. We had a lot of erosion right after the installation. We had a lot of sediment fill up these basins. And then for all those folks that have WASCoBs out on their fields, you know that there may be some early maintenance. You know, in the first couple of years, you might have to clean them out. I've been walking a lot of fields lately, and I see some of these standpipes that are sticking out 6 or 8 inches from the ground. So there's a lot of sediment buildup in some of these systems already. Cover crops panel, close your ears. That's our establishment of our cover crop one of the years. So we were a little late in getting that planted, but it was due to the harvest. We should have had an airplane or air seeder or something fly it on. So some of the soil sampling we're doing, we're looking in the basin, and what we're trying to do is just take nitrogen and phosphorus accumulation, and we're taking bulk density samples to get a total mass of the sediment coming into these things and to calculate loads of nitrogen and phosphorus in these. So some of the loading we're looking at, you can see on the bottom ones, the cover crop didn't really have an effect at all. Like I said, close your ears. But it was due to poor establishment, and you know, it was only 1 year of data. There was 1 good year of data, and then we had poor establishment. So it takes a few years for these to really show an impact. And we did have a lot of soil disturbance in the installation of these, and this was following year 2 of the installation. But we did see an impact of the actual dry dams and WASCoBs. We saw pretty big reductions in terms of nutrients and sediment. And when you look at the red circles there, those are the ones that ephemeral gully was much higher than the others in terms of retention. Trapping efficiencies, we're seeing trapping efficiencies almost at 100% in terms of sediment, pretty high for phosphorus, 30-40% for nitrogen, which you'd expect with nitrogen because nitrate moves more readily through the system in the water. So the other things tend to settle out with the sediment. So the crop yields. If you remember that map of where the WASCoBs were, you can see all these red areas. Those aren't good. Those are the crop yields that were very low during that time of year, or during that year, that season. And those are in those areas that were highly disturbed by a lot of movement. So again, when you're putting these WASCoBs in, some of them are designed by USDA. A lot of farmers will put them in on their own. But there's kind of this balance between how much soil you got to move versus the tile size. You know, if you got to put a great big tall 6-foot berm in there, you got to move a lot of soil to do that. And that's where you're going to impact these crop yields. So to summarize the cover crop part, we had no impact on the cover crop at all during the first 2 years. We expect over time that we will see an impact. The WASCoBs themselves significantly reduced nitrogen, phosphorus, and sediment. And then the trapping efficiencies, like I said, range from 32 to 80% for the nitrate and ammonium, and then upwards of almost 100% for sediment and phosphorus. And then the corn yields were impacted. So some of the future research we're going to do with these WASCoBs is we're going to sample a lot more of them closer to home. This is a 4-hour drive for us to this Atterbury site. So if you look at the counties down there, That's right around Carbondale. We're looking at Jackson County, Williamson County, Union County, and Randolph right now. But we're going to select a lot more of them and sample them much more intensely. 5 or 10 of them, we're going to put water samplers in and try to capture how much, looking at water quality, trying to assess that. But all of them we're going to fly with a drone. So there's a lot of different things we're going to look at. Some of our dependent variables are going to be just the water chemistry, the legacy nutrients, nitrogen and phosphorus, and this is a little more short term than what we talked about this morning, and then legacy sediment. Some of the independent variables are going to be WASCoB age. So we're going to take some that have just been established. We've got some that just went in this fall, there's nothing on, and then we've got some that are upwards of 30 years old. So we're going to look and see how WASCoB age impacts water quality. The cover crops, the crop rotation, the tile and the orifice size. Like I said, if it's a farmer that puts it in, typically the tiles are a little bigger in diameter. They're trying to get that water off faster. They're slowing it down, but they want to get it off out of the system. And then we're also going to look at the physical site characteristics, so drainage area, soils, the slope, and things like that. So we're going to do some drone surveys. We've got this fancy Phantom 4 drone with RTK, so it's tied in to these satellites. It's got centimeter accuracy. We're going to be able to fly over these things. You can see the tracks in the field. We're going to use some Pix4D software to analyze this. And the Department of Transportation, you know how good their road system is? They use this same system. So good stuff. But it's to look at cut and fill, how much accumulation of the material there is or how much erosion there is. So we're going to calculate catchment area. With this drone, we're going to get a real accurate digital elevation model. And then we can look at basin fill for both water and sediment accrual. So you can zoom in, you can see tire tracks, and this is going to be in Pix4D. So these are just a bunch of aerial photographs that are stitched together that we can look at today. We can fly it in another year and look at those again, and we can see exactly, well, hopefully exactly how much sediment has been accumulated. If we can't get an exact on the sediment accumulation, what we are going to get from this is a very accurate watershed area, drainage area, and a fill. So how much water is coming into this thing? Or what's it look like when there's a foot of water in it? What's it look like when there's 2 feet of water in it? And this is an example of that, what it would look like. So, redneck ingenuity goes a long way with me. So if you look at these apparatus up here, many of you will recognize that one on the left as a trail camera for deer hunters, right? So what that thing's set up to do is every hour it will take a photograph of that staff gauge. So every hour we're going to have a stage. Instead of, we want to sample as many of these as we can. So instead of spending $80,000 for ISCOs and pressure transducers, we spent $150 on a trail camera, and we got some PVC pipe over there with ping pong balls in it. So what's going to happen with those, that's kind of our retrofitted example of our stack pole sampler. Those little copper tubes tend to get insects in there, and they build nests, and they always got plugged up. But these, what the ball does is when the water comes in there, it floats up, and it's tapered at the top, and it won't allow any more water to come in. We've tested these things 1,000 times in the sink and out in the field, and it's not letting, every time you push that ball down, it kind of belches out the air, so we know it's not getting any more water once it gets past that point. So we'll be able to set the elevations on these to take water quality samples. And I feel real bad for my grad student. Have you ever been into the store, and you probably have bought 100 ping pong balls at one time? No. He's not, they look at him, he's not playing, Forrest Gump in the Olympics or anything. They're thinking, man, this guy's got a beer pong league going on or something. So that's what our students have to deal with. But anyhow, in the basin, we're also going to sample the sediment again, look at bulk density. We're going to do this in transects, but we're also going to look at nutrient accumulation. So how much nitrogen, phosphorus, what's the legacy amount, what's getting trapped in there? And we're going to tie this all into the age of the WASCoBs and some of those other characteristics I talked about. So Karl, it's your turn to come up here and take over with the gypsum study.
Thanks, Jon, for that. I'm going to talk about our last project he mentioned, our gypsum project that we started 4 years ago. Impacts of flue gas, desulfurization, gypsum application on water quality. We also looked at grain yield on 2 private farms and at SIU. I'll have some brief results on that as well. But Dipti Powdle is the current master's student on this, and she did the bulk of the work. I'm, of course, advising and helping and mentoring, but she deserved to be on the front there. So our objectives were to look at these FGD gypsum applications and their impact on dissolved phosphate and total phosphorus in runoff, and we did that at the SIU farms. You can see, again, a drone shot of our setup there where we had corn and soybeans grown up top, and then we were collecting surface runoff in some flumes and some dustpan collectors, funneling that into some barrels that we collected the runoff, and then also collected samples for water quality analysis. And then we were also looking at the impact of the gypsum on grain yield. So again, our experimental design, we applied 3 different rates of gypsum, and that gypsum, we got that from Prairie State Energy. We did 2 different applications, one in 2018 and then one in December of 2020. And for those who may not be familiar with gypsum, what we're talking about there is calcium sulfate, and that's a byproduct. So when you produce electricity from burning coal, you tend to have some sulfur emissions, especially in southern Illinois. Coal, not like where I grew up in the anthracite coal region. The hard coal was a lot lower sulfur coal. But so to scrub some of that sulfur out, we tend to they put in lime in there. So the calcium combines with the sulfate. Hence, we get gypsum as a byproduct, and that can be utilized as a soil amendment for sodic soils, but we're looking at it, of course, for potential water quality benefits on phosphorus. So our methods, again, we applied December 2018, and then we came back 2 years later. Now, that's not typical. This was for experimental reasons. Generally, a producer would do this every 3 to 5 years, an application cycle. And we collected those runoff samples after every significant rainfall greater than a ½ inch and looked at DRP, total P, total suspended solids, and also sulfate. And then also measured the total runoff. So quickly, our results. So I'm breaking this into 3 different periods. So we had the initial post-application period, so that was in 2019. So we applied December 2018, and we went till May 2019. And at that point, we did a phosphorus fertilization. We put 100 pounds of DAP on, so that added, about 20 pounds of phosphorus to the system, and that sort of ended that first look at the phosphorus in the runoff, because it sort of swamped out some of the effectiveness of the gypsum. But you can see here, it was working fairly well, that first application cycle. We got on total phosphorus, we got approximately a 40% reduction in the 1 ton per acre rate and the 2 ton per acre rate. And those are the recommended rates by USDA. The 6 tons, of course, that's for experimental purposes, see what happens if we load up this system with gypsum. DRP, same thing. We got some, on DRP loads, they were reduced by 35%, 45% on the 2 tons per acre rate. So did pretty well. You can see the numbers. Thank you, Andrew. He gave us our hot spot for phosphorus export was 1.8 pounds per acre. We're sitting well above that. We're probably losing about some years 7 to 8 pounds per acre on our southern Illinois soils. A lot of runoff. We tend to have relatively high phosphorus levels in those upper soil horizons. So this is if you see the load side there on the right, that is a mean for those different events, and we Dipti sampled 14 different events, so that's about a ½ of a pound on average on losing every one of those events in the control system. And then, of course, you see the The other ones, they dropped by down to 0.3 in both cases for the 1 and 2 tons. So there was a good reduction there. And also point out, you can see the runoff. So if you look to the left, you can see the runoff in the control plots and then the gypsum plots, and that was reduced as well. So that we're thinking, there's evidence in the literature talk about clay flocculation by gypsum improving runoff rates. That definitely in this first application cycle seemed to be the case at our site. So this is from the post-DAP fertilization period in 2019, and that goes up to November of 2020. And you can see much different story. And what we think happened, of course, is we're adding a decent amount of phosphorus to those soils with the DAP, and that probably swamped out any remaining effectiveness of the gypsum. And we saw some a little bit, but much different than that first application cycle. Then we had Dipti come in to do her thesis work. So we did this second application cycle and what you see here. But this time we did not apply any DAP to the system because we really wanted to see, well, how long is potential effectiveness of gypsum going to occur? We only had a 5-month look at it the first time around, so we wanted to take a year look at it the second time. And you can see we did see some total phosphorus load reductions, 47% in the 1 ton and about 15% in the 2 ton in terms of load reductions. There's also concentrations there as well. But we didn't see a DRP reduction in terms of the means. But if we look at these trends, so this is just the plots of those points that Dipti collected over time in 2021. You can see at first, those first couple months, there were some significant reductions, but what happened over time, you saw those DRP levels creeping up there the whole time. These send slopes are all increasing, they're significant. So you can see later in the year, we saw much less effectiveness of the gypsum. So that, we can use gypsum potentially as a tool, but its effectiveness, certainly even over an annual time scale, is probably diminishing as we go along. I didn't talk about the sulfate, but as you expect, when you apply calcium sulfate, that disassociates, right? So you have a lot of available sulfate in the soils, and we saw that, we measured that in the runoff. We captured a lot of sulfate, some pretty high levels, but that did decrease over time that you see here. And then one of the concerns of applying any of these coal combustion products, of course, is potential heavy metal contamination. So we did send off the actual gypsum we applied from Prairie State. We also took soil samples. We also took runoff samples. And you can see this is some of the soil sample data for different heavy metals. And you can see all of those were well below the EPA standards. Most of them, if not all of them, were actually lower in post-treatment than pre-treatment, except for nickel. But you can see the post-treatment was actually lower than the pre-treatment. So we can say with pretty good confidence, at least the gypsum we were using at the site, we were doing it in that heavy metal contamination is not going to be an issue. But that is something you want to test. If you're thinking about utilizing gypsum, we would recommend that you have the product tested. And then quickly on the grain yield results, we went out to Besego Farms in Freeport, or Freeburg, and then up to, and I know John will kid me for this, but Kinmundi, the Webster Farms, and then at SIU. And we looked at grain yields after applying gypsum at different rates. And we gypsum plus lime plus sulfur, and at the same levels of sulfur and calcium as you would be supplying by the gypsum. And we didn't see, as you see here, a lot of variability in the yield, no significant differences among the treatments or control for grain yield. So it didn't have a positive, but it didn't have a negative impact. And one of the thoughts is there's potential sulfur deficiencies because of the Clean Air Act, scrubbing a lot of the sulfur out of our stacks, right? So we're greatly helping the acid rain, acid deposition problem, but some producers, we're hearing about sulfur deficiencies in crops, so that's something we wanted to test here. So you can see I went through a lot of this discussion, but sort of a summary that you can see. And one of the big ones is that phosphorus really swamped out the effectiveness of the gypsum, but we did see effectiveness on that, that first 5 to 12 months. We're definitely seeing some reductions in phosphorus. And then some of the conclusions, Dwight Sanders did an economic analysis for us looking at the gypsum application. And what he found at the 1 ton per acre rate in our standard corn and soybean rotation, it reduced phosphorus loads by about 2 to 3 pounds per acre per year compared to the control. So that's pretty good. And the cost of that phosphorus removal from runoff averaged about $3 per pound across the study. And that's pretty economically efficient, especially compared to some of the other phosphorus removal strategies. So that's something maybe in the future we'll be sending to Reed's committee, looking at. So I appreciate the work you guys are doing. That's really good to try to get some more practices on the nutrient loss reduction strategy worksheet. So just some acknowledgements. Really thankful to NREC for supporting this research. Illinois Farm Bureau, NRCS, so a lot of folks, Mary Auth on there, as John said, the land improvement contractors. And I know we're over time. John, actually, he was the long-winded one today. And I kept aside.